Okay, let's start. So now let's talk about multi-hop networks, but this is the kind of iteration that we had here. I just tried to have it pictorially. It's something like that. So individual worker, they're gonna send their AIW1K. So they're part of gradients or part of the subgradients. Why? Because this actual subgradient is something like that. But a portion of their gradients, and then to the master node will run this guy and then send back lambda k here. So you can see that in order to be able to run that, there should be a master node that gathers all these to be able to find the subgradients at that point. But what would happen in multi-hop networks if we do have a topology like that? Topology means that the communication is only allowed with this specific structure that is given by something called communication topology. So in that case, definitely you cannot run these form of iterations, because in this form of iterations, we can run that only for this specific node, for instance, or the other node, let's call them cluster heads. We can run them here and here, but then it's all locally. Okay, so what we should do here in this setup, and how we can again do this form of dual decompositions or primal decompositions in this setup. So in general, distributed optimization. So we need some definitions here. So the definitions, let's start first by something called a stochastic matrix or row stochastic matrix, which are the set of squared matrix, positive matrix. So individual elements aij should be positive for all ij, so positive matrix. And they should have 1 as their right eigenvector. So a1 equal to 1. What does it mean? It means that if you sum up over, let's say, A to B, ai1 for row I, I2 up to ain, then the summation of these guys should end up to 1. So this summation of aij over j should be equal to 1 for all rows. So these kind of matrices are called stochastic matrices. But then from Markov analysis or Markov theory, we know that these form of stochastic matrices with these definitions, they are defining some Markov process. And what is the Markov process here? This I is like an state I. You can call that. We will need this form of Markov interpretation here. So you have that, and from this node I or state I, you can go to all state j. So state 1, state 2, up to state j with these probabilities ai1, ai2, aij. Okay, so this is an interpretation of this form of matrices. So this is only for state I, and then you can have the same thing for all other states as well. So these stochastic matrices, they are defining a Markov chain or Markov process, let's say. Doublet stochastic matrix is a matrix which is stochastic itself, and its transpose is stochastic as well. So transpose is stochastic means that it's both row stochastic and column stochastic. Okay. So these are called doublet stochastic matrices, and they do have some very nice properties. So why we are having them? Because later on we will see that we can make this problem, we can transform this problem in the problem of optimizing over some of these stochastic matrices that we can define. Okay, so we make sure that we do have these nice properties. And okay, so wherever you do have this, you can now just interpret this guy, this Markov chain, as a graph with some edges and some vertices by defining these guys as vertices and these guys as edges. That's it, very easy. This is the usual way to define undirected graph, but then you can define directed graph as well. So why directed and undirected? Because here the communication is undirected. Communication means that there could be some form of signaling in general sense, some signaling between these two nodes, for instance. This is undirected means that both of them can communicate. So this guy can send something here and get something from that or receive, but then it could be directional as well. Okay, cool. With these definitions of Markov processes, we can say that I and j is an edge of this graph. Okay, I and j means that there should be a link from I and j. So this link here, so this is a link, belongs to the set of edges of that graph if this is undirected. So if j and I is a link as well here. This is just for some technical reasons, that there is a lower bound for those values. We know that eta is equal to 0 by definition is a lower bound, but there is some positive things. If they are not 0, then they are larger than something, so they cannot be infinitesimal any value. So there should be a small positive eta. So either they're 0 or larger than some eta. Okay, so why there's 0, for instance? It could be 0. It means that if this is 0, then there is no link here. So there is no probability that go to transit from state I to state 2 in that case. It means that here this guy is 0. Okay, so this is just very simple interpretation here. Then set of neighbors of vertex I is all the nodes, including node I. So this is by assumption that from node I, we can reach node I. Okay, so what does it mean? It means that ai here should not be 0. Okay, so we can reach node I. The meaning in terms of optimization is that all those, they are local variables, so we should have access to those local variables anyway. And this is the set of all the nodes that are reachable in one hop from node I. So this is the definition of this set of neighbors. And then the degree of a vertex is the cardinality of this set. So the number of nodes, including node I, that we can reach. So definition of the degree of a vertex here. By the way, let's define this A. What is the meaning of A2 of ij? A2 of ij means that the probability of transiting by this Markov analysis, this is the probability of transitioning from node I in 2 hop to node j. So if there is no link here, but then there is some positive things here, of course there could be some positive from here as well, okay? So that probability somehow mixes the probability of 2 hop, transitioning in 2 hop from I to j. So this guy and that guy. Something like that. Okay. Why this is important? Because now you can realize that for this specific graph, which is called 2-star graph, if there is no link between one side of that graph and the other side of the graph, so it's like a bipartite kind of graphs. So if there is no direct link, then you may be able to form something like A2 with the hope that the communications, you can exchange the signal in 2 hop. This is the meaning of that guy with some probabilities. And then, of course, you can exchange with 3 hops and 4 hops and all those kind of things. In general, we can define AK. AK, by the way, is AK times. K times product of this A. So this guy. Okay? So here you can see that lack of one master node somehow by these definitions can be somehow compensated by more and more rounds of exchange. Again, and the underlying assumption here is that we are allowed to do only 1 hop exchange of information. So we cannot directly send anything from this guy or this guy to that guy. This is by definition of this topology here or this graph. They can be geographically very separate, they're far from each other, and they cannot communicate, for instance. So they need to communicate through this guy. So this is the minimum distance between these two, for instance, 3. Okay, cool. Now, let's go to real distributed learning setup. This is our famous problem, 1 over n summation of all I of fi. And then we see that how we can solve this problem, right? So how we can solve this problem? What we have seen so far is the closest one to this problem. The closest one to this problem is 1 over n summation of fi of wi subject to ai wi equal to b. We know how to solve that with dual decomposition. Solve that, I mean, in the distributed fashion. We know how to solve that in dual decomposition, right? So can you use this and the warm-up example that we had to address this unconstrained optimization problem where we do have only one coupling variable W? Yes, we do. What we did there was to introduce, if you remember, we had f of W1 and V plus f of W2 and V. So what we had there, the trick was that introduce two different variables and then another constant V1 equal to V2. Okay? So now you're combining this warm-up idea with this general form of dual decomposition with linear constraints. We can write it down, this problem, with P1, which is just adding, replacing that coupling variable with local variables Wi and adding a consensus constraint. And making sure that Wi equal to Wj for all j, so all the workers, all n. Okay? But this could be hard. This is, and now you can run dual decomposition on this guy using master worker strategy, as we have already seen. Because Wi equal to Wj means Wi minus Wj equal to 0, so a set of linear constraint. Again, you can define A, you can find A and B in for this case. But what's the problem? The problem is this. This could be very hard in general, in the sense that we need a master worker strategy. So what we should do if we want to limit ourselves to a communication graph like that? So in that case, what about just replacing that red part with this blue part? So just make sure that we have consensus over our neighbors. So the physical meaning is that we need to have this consensus for this guy. For instance, we need to have consensus between this and that. For this guy, we need to have consensus among all these, including itself and that guy. So consensus among the one-hop neighbors. So this is the meaning of this constraint. But can we say that these P2 and P1, they're identical? In general, they may not be. One simple example is like this. So having this, then you can easily show that P2 is not identical to P1, because there is no way that there should be necessarily a consensus between these two separated graphs. Okay? So here you can imagine that there should be some form of connectedness in the graph. So something like that. So then we can show that in the simplest version, we need to have a connected graph G. And if we do have a connected graph means that from every vertex of that graph, there is a way to some other vertex. It doesn't have to be a single hop. It could be multi-hop, but then there is a way that go from every graph to other graph. Or the Markov chain should be irreducible in general. So for connected graph G, P1 and P2, they are equivalent if this graph is connected. What would happen if it's not connected, but let's say the graph is not stationary? So here the assumption is that the graph is stationary. So this graph that you are seeing, this is a stationary. So this is there for all rounds of the communications, all rounds of the iteration. Again, remember that we need to iterate over K. So we need to have a lot of rounds of iterations, and in every iteration, the graph is there. What would happen if the graph is time variant? So over time, it changes. So then we cannot say, well, one easy say is that all those set of graphs, they're all connected. Then we can satisfy this. But there are much more relaxed version of that by saying, so for instance, one of them is like this. So the graph should be B-connected. And what is B-connectedness? It means that the union of graph 1, graph 2, so the graph at time 1, the graph at time or iteration 2, up to the graph at iteration B, this union, this forms another bigger G, and let's call it this, I don't know, G bar B. And this G bar B should be connected. And if it is connected, then we can show that solving P2 would be identical to solving P1. But then here you can just imagine that it could be much more complicated to solve this guy in terms of more computations and more rounds of iterations. It might be, okay? Question?
If Ni is one hop neighbor,
Mm-hmm.
then how will this equivalent disconnect? N is the full nodes, yes? And Ni is one hop
Mm-hmm.
neighbor.
Mm-hmm.
I don't understand how they could be equivalent if it's still disconnected.
Okay. So
You're losing some information.
Yes. So the question is how we can make sure that connectedness over the graph G makes sure that P2 is identical to P1. The thing is that P2 is not identical to P. Well, these are equivalent in the sense that the solution that you will find if you run this optimization problem over. At this point, we didn't say how we can solve this optimization problem, right? We will see that in the next slides. But it just says that if the problem satisfies connectedness over the stationary graph, if it is stationary, some other assumptions as well. But in general, the solution that you will find here would be identical to the solution that you will find from there. And then the whole idea is that there is a way, this connectedness makes sure that there is a way to reach that consensus. So this is a globally consensus among all the workers, and this is a local consensus. But since the graph is connected, then at the end, just imagine that we reach some points, okay? So let's say that the optimal solutions is W1 star should be, or W1 star should be equal to W. Okay, let me even make it more concrete. Let's consider this graph. Okay. So these two star topology, for this guy, this constraint says that this W1, 2, 3, 4, 5, 6, and 7. This says that W1 star should be, whatever the optimal solution here, should be equal to W4 star. And then that constraint for 4 says that W4 star should be equal to W5 star as well. Also, it should be equal to these guys as well, okay? But then W5 star should be equal to W6 star. So transitivity of these equalities makes sure that we do have a consensus at the end. But what is the price? The price is that if we did have a master node, we could do that, these form of consensus in one hop, in one iteration. In one iteration, we could make sure that all of them are identical. But since we don't have that, we may need a lot of rounds of communications or a lot of iterations to make sure that the information will somehow diffuse throughout this graph, okay? A much simpler form of this problem is called the classical average consensus. In that problem, the only thing that I did is that I just removed the objective function. So there is no objective function, and the whole idea is just to reach a consensus over the graph. So one specific example could be like application, could be we do have different sensors, and the whole idea is just to have an average temperature of the room, for instance. So different sensors, they measure different things, and then there is no central controller that takes all those values and then easily find the average gradient, the average values. So in that case, we can just write down this optimization problem, constraint satisfaction optimization problem, and then we can equally write down to this optimization problem, right? The only change that I did is that I just introduced this Aij here. So why we should do that? You can easily see that any feasible point here is a feasible point there, and then the same. So any solution here is a solution here, and vice versa. But then introducing Aij can really speed up the whole process of solving this optimization problem. So it has nothing to do with the reaching the optimal point, but it really can improve the convergence rate, how fast or how easy you can reach that point. So this is the whole idea of having this Aij. But now you can just get the connection to all these things that we have mentioned about the stochastic matrices and all those kind of things. Okay, so this is the whole idea of introducing Aij. And then we will say that these Aij are coming from some double stochastic matrix, so row and column stochastic matrices compatible with G. What does this mean, compatibility with G? It is essentially the assumptions that here we have set here. So the compatibility with the graph, and compatibility means that if there is no edge, set Aij equal to 0. Okay, so here we are. So we are saying that this is for all j belonging to set of all neighbors of I, but what would happen if some j is not in the neighbor of I? We can choose any ij, right? So this says that let's try to make these AI compatible with the graph to make sure that now we can drive a Markov chain for that. So if there is no edge, then set Aij to 0 in that case. So then we call this compatible with the structure of the graph or geometry of the graph. And then for this specific optimization problem, let's just do this very simple iteration. So wk plus 1 is a wk, and a is the set of all those, not the set, is a matrix that is created by those aij. Then in that case, this very simple iteration, you can easily show that you can converge in a linear rate, and this sigma 2 is the second smallest eigenvalue, singular value of A, so eigenvalue of A transpose A. And you can converge to this, to where this is WK, okay? This is the point to which you will converge. This is your initial guess. Well, the difference between initial guess and, let's call it W star, or I don't know, whatever. Let's call it W star, this guy. So now you can see that W minus W star is smaller than something to power k, so linear rate, W minus W0 minus W star, so the initial guess. So what is the meaning of this AW? So this is general for any general A. Again, you have the freedom to choose A. As long as it's double stochastic matrix, then you have this convergence. Okay. So now in the next slide, we're going to see some specific examples of choosing this A. So this is the optimization problem that we have. And one simple way to choose that is just Wij, this A is equal to 1 over n of summation of the over neighbors. So essentially average out only over your neighbors. So let's consider again the same topology of two-star graph. 1 through 3, 1, 2, 3. So this two-star graph, 5, 6, yep. So it says that at every iteration, k, just go with 1 over, so this is di, right? So 1 over di, the degree of your connectivity, summation wik. That's it. So just look at your neighbors and average out the values. So let's run that algorithm on something like this. So here we have 3, 3, 3, 0, 0, 0. So W0 is 3, 3, 3, 0, 0, 0. Well, it should be a column vector anyway, but that's OK. So this is your W0. This is the initial point. And then we want to see if we can reach that optimal point that we have seen here. So this is the optimal point. By the way, what is the meaning of this optimal point? This is the consensus, right? So this is the average over, this is 1 over n. So this is the average over all values. Multiply by a 1 vector here, or column vector of all 1. Essentially, it means that all the values in that WK, they should converge to the consensus. And what is the consensus? Consensus in that case is the average of this. So essentially, this optimization problem, if you solve that, it says that Wi should be all equal to Wj. So if you start from this point, what is the final point here if you run this iteration? It should be, we know that W infinity, let's say, it should be 9 divided by 6, so 1.5, 1.5, 1.5, 3, 4, 5, 1.5. So that should be the final solution here. But just to see how we can converge, we can just do some iterations over that with this special case for A, which is averaging out over just the neighbors. So, so what is W1? And for sake of simplicity, assume that at iteration 1, we just do that for node number 1, iteration 2 for node number 2, node number 3, then 4, 5, 6. For node number 1, it's going to be the values, the average values with respect to only the neighbors. So the neighbors of 1 is just these two, right? So that's going to be, and no change in other values. So then the vector is going to be 3, 3, 3, 0, 0, 0. But you could guess that, right? Because if the only communication is between these two guys, they do have agreement anyway. So there is no change in the vectors. The next iteration is updating 2. But what would be the value? The value would be, again, the same as W0. Why? Because there is a consensus between these two anyway. So there is no need to have any change. But now, if you want to update this, then you will see that there are going to be some change. So there is no update in 1 and 2. So the values are the same. But then the value here is going to be the average of this guy, this guy, this guy, and that guy, right? So it's going to be like 3 plus 3 plus 3 plus 0 divided by 4. So now we are reduced from 3. So now you can see that there is a dissemination of the information from this part of the graph. And then you can imagine that this is one of the hardest examples here because there is just one edge between these two completely different communities. And it starts with a very extreme case where all the points, all the workers, or all the vertex in that community, they do have a strong belief on 0, okay? A strong belief on some party, and a strong belief on 3. So completely different beliefs. So that's why this problem is really hard to solve. But then here we have this, and then 0, 0, 0. So here you have a smaller value. But then in the next iteration, iteration 4, for this guy, then they're going to be average between 0, 0, 0, and this value, which is like this. So the value of this guy will be a little bit higher. Then we have the next iteration, which is going to be the consensus between these two. And this value is already higher than 0. So if we just run that, let's see, I do have here up to x7. So if you run that for 7 iterations, so just one round of the iterations, then we're going to have 2 points. Why in 7th iteration it's going to be smaller? Because in iteration 7, we have one round of update over all the nodes. And we have already seen that the value here is smaller than 3 now. So it means that the next iteration, there's going to be an average between 3 and this value, which happens to be 2.62. And then the next one, but there is no update here so far. There is an update here, so let me just pick it up. 2.25, 5.6, 2.28, and 0.28. So now you will see that after 7 iterations, we are closer to the consensus than the starting point. And if you just run these iterations over and over and over, you're going to reach the consensus. Okay? And again, this is a very complicated example. You can, in general, you don't have these form of complications. So after 7 examples, probably you are more closer to the consensus. So this is one simple iterations. So it's one simple choice of A, which should be something like that. Okay. Just as a homework for yourself, just make sure that this A that is defined by this summation, so average over set, it satisfies the double stochastic property and compatibility to the structure of the graph. So because we should satisfy that. Then gossip algorithm, which is very, very famous kind of algorithms, very useful when we do have some form of asynchronous updates, okay? So in gossip algorithm, it's really clear from the name, very cool name, by the way, for that. It essentially says that at every iteration, here we do have our graph here. So at every iteration, just randomly pick one of your neighbors. In general, you can pick a set of your neighbors, in this case, S. So a subset of your neighbors, just pick them at random and update based on the average over set. So the main difference with this guy that we have done already is that at every iteration is like the difference between gradient descent and subgradient descent. Gradient descent, we do update based on all the gradients variables or all the gradients. And in subgradient, we just randomly pick some of them and do an update based on that. So Monte Carlo approximation. Exactly the same idea here. So we do have a Monte Carlo approximation of the previous algorithm. And then, as you have already seen in a stochastic gradient descent, under some assumptions, we can converge here exactly the same things, but then we can converge linearly, but in expectation. Why in expectation? Because at every iteration, we're going to pick some random set of edges to consensus or to do the update. But so due to those randomness, at the end, we need to have a little bit different version of consensus or convergence. Anyway, this is another iteration, so I can take it down. Again, you can check that this guy, this choice, will satisfy the property of A being doubly stochastic. But then what's the main difference? The main difference is that here you may not be able to show that all the graphes that you are making, all of them are connected. So some of them may not be connected depending on your choice of selection. But then the thing is that the union of all of them should be connected, or their average should be connected. So there are lots of different versions of the convergence depending on those assumptions, okay? Cool. And then another form of iteration that again satisfies this property for A, which should be doubly stochastic, is called lazy metropolis iterations. It's lazy only because of these two. So if you remove these two, then you're going to have metropolis iteration. But then it turns out that adding that two will have a lot of theoretical benefit. Makes everything much easier. So WK plus 1 is WK plus, instead of having an average over the set of neighbors, we're going to have an average over, well, multiplied by 1 over 2 is not really important, over this maximum of my degree, di, which is this iteration, and dj. So that's it. And then this guy, Wj minus Wi, which is one step toward the gradient distance. So it's essentially trying to write down this guy, put that somehow in the objective function, or define a quadratic penalty of violating Wi not equal to Wj. Try to add that, and then write gradient distance for that, and then you can just get this form of iterations. Okay, cool. And then we can have, again, linear convergence for this. Again, remember that all of them are for solving this problem. Okay, cool. So now let's look at some graphs, communication graphs. We already have seen some example for 2 star, but this is the meaning of topology dependent convergence rate. The underlying assumption is that you are limited to have only one hop communication. So if you want to diffuse something from this very left node to some very right node, then you need to undergo over 1, 2, 3, 4 rounds of iterations, at least, in the best scenario. But this is not usually what usually happens. Because in the consensus scenario, for instance, in the first iteration, this information here will be mixed out with the information here because we have one step communication. In the next round, the information here will be somehow mixed with these things. So at the end, the information that this guy will get is a mixed up all the informations here plus alpha k's plus lots of those things, okay? For past graph, which is the first one in the left, the convergence usually is, for that consensus problem, with using lazy metropolis iterations. For the past graph, the convergence is of the order of n squared. So we usually know that if we have log of e to power minus 1, this is linear convergence rate that we had, but then we need to have a penalty of n2 in the worst case. And this penalty of n2 is due to lack of this central controller. So if we did have that central controller, that master node, then we didn't have that penalty. And n is the number of nodes here. For 2D graph, like this one, then we have n log n. So a little bit faster diffusion of information. For a star graph, the way that you will find this is usually based on that. So it's usually based on this, and based on that, and something called a spectral norm of the graph. So the second largest eigenvalue of the graph, and based on that, you will bound that second largest eigenvalue for these type of graphs. So this is the way that you will find these n to all those dependency. For a star graph, which is a very great one, unfortunately, these iterations says that we do have this. But why? So we need to have a penalty of n2 in general. And there is no difference between a star graph and 2 star graph. But then we already seen that for a star graph, we can have a very great iterations. The main problem, though, is that in that kind of communication, we ensure that since the graph is a star, we ensure that we don't do any update here. So there is no update here. All the updates will be done here at this master node. Whereas in this case, we do some update here, and then we do update here, here, here. So in all those children's, and then we do have another update in the parents. So this is a problem here that we didn't have in dual decompositions or even primal decomposition. So there is a master node that really updates everything centrally. This is not the case here. Okay, cool. And then we have geometric random graph, which is a random graph, but then determined by some geometry. So from every edge, there could be some link with some probability to some, from every vertex, there could be some with some probability, some edge towards some other vertex, as long as they are sufficiently close, so they are within some bounds of distance. And for complete graph, this is order of 1. Why? Complete graph means that there is an edge from every node to every other node, or every vertex to every other vertex. The reason is that there is just, in one iteration, it just doesn't matter from which node you're going to start. From every iteration, you have all the global information, and then you can run one iteration, and then there should be a consensus there. Okay, so that's why it's order of 1. Okay. So now let's try to look back to our objective, our main problem. So again, this problem was just minimizing 0 subject to this, so only average consensus problem. But now let's try to look at our problem, which is a finite sum subject to consensus here. Okay. So in this case, we can both look at primal domain or dual domain. Okay. In the primal method, there is a famous decentralized subgradient methods, which essentially what it does, it just generalizes that primal decompositions that we have already seen in the primal domain. So try to make distributed optimization of this guy in the primal domain. In version 1 of this algorithm is we do have 2 rounds of steps. Again, in the first round, we do have this consensus iteration. And in the second round, we're going to have a subgradient descent. So what is in the consensus, we have seen already that, let's first look at this guy. So this is the consensus form here. And if we compare this guy with these iterations, for instance, this iteration essentially says that in every iteration, go look at the variables of your neighbors and then try to reach consensus with them. So this is the whole meaning of this iteration. Here, we do have the same. So at every iteration, there is a balance between reaching consensus, so meeting the constraints, and improving the objective, so going downhill with respect to that consensus point that have achieved. And this GI is a subgradient. If the functions are differentiable, then you need to replace that with the gradient of the functions I. But then this is local. Why? Because, so it means that here we can do that in parallel for all the nodes. In parallel for all the nodes means that the only information that you're going to need here is just your local information. All the informations that are available in one hop neighbors. So just find the value, get the value from them, take an average, and then minus alpha k go downhill. 2 points. The first thing is that you can imagine that you can see that this wi, it is not a function of k in the sense that, well, these aij's in this specific case of a stationary graph, they are not a function of k in the sense that you're going to combine the values from your neighbors with the same weights in all iterations. The weights are subject to change, but then the parameters are subject to change, but the weights are not. Whereas the going downhill is subject to change with respect to alpha k. So at the initial steps, especially if you choose alpha k not to be constant value, but just to be a square summable but not summable and decreasing iterate sequence, then what happens is that at initial iterations, you're gonna go really downhill. So try to optimize locally, and after some point, try to reach consensus. Okay, so you can do that. But then here, if you run this, you can converge. So I said that this one. And then the thing is that it's like similar, as I mentioned already, similar to diffusing or mixing time as consensus, because the main iteration is like this one. And the time that it takes this guy, here, after some points, this guy is going to be very small, and this is the main complexity here. So how time it takes to diffuse over that graph. Okay, cool. And then we can have version 2, which is like that, is almost similar. So we have the same term here. So in the version 1, we have the same term here, average. So the consensus here, consensus over AII, WII, so your specific value, plus weighted sum of your neighbors minus alpha k gi evaluated at your value. So this is the main difference. Either you want to evaluate that at your specific value or your specific parameter, or evaluate that gradient or subgradient at the average point. So this is the main difference between these two. Fundamentally, not so much. This is the last slide, I guess. Distributed learning over undirected graph again, but so we have seen that you can run these form of iterations. The convergence analysis here are usually harder, actually much harder than the normal gradient descent, simply because of diffusion over the graph. They are more involved, that's it. And that's a primal kind of decomposition, but here you can do the dual decomposition as well, and this is homework 3C. So you have seen all the elements, and you can use now the tricks. I'm not sure if I do have that. No, I don't. So you can use the same tricks as dual decomposition in the warm-up example, dual decomposition over a graph of master-worker scenario, and then how you did this primal decomposition here. So combine these three to see how you can do dual decomposition here. Just final comments on these distributed optimization is that in the next lecture, you're going to see another dual approach, which is somehow a generalization of dual decomposition. It's called ADMM, Alternating Direction Method of Multipliers, very famous algorithm. It usually have, as we have already mentioned, augmented Lagrangian term, which is just this square or quadratic penalty of the constraint function to the objective. You will add that. And in a very high level thinking, it's a combination of dual decomposition. You will see that in your homework 3C, how you can do that. Augmented Lagrangian, which is this guy, and coordinate descent. This is a combination of all these three terms. You will see that. And then later on, you will see how you can do that over network. Because generally, this form is suitable for master-worker scenario, but then how you can do that over the network. Pretty much similar to how you did that in decentralized subgradient method. OK, we didn't talk about directed communication graph, but fundamentally they are the same. They're just a little bit more involved to make sure that it's strongly connected. The graph is strongly connected means that there is a link, or there is a path between nodes I, vertex I, and vertex j, and there is a path between vertex j and vertex I. That's it. So the assumptions are a little bit stronger. Algorithmic parts are almost the same. Latency in communication links, so far we just said that there is a cost here in terms of n, in terms of the number of times that you need to go over that graph, but then there could be some other penalty like latency or faulty communication link. And faulty communication link means that you can handle that with gossip algorithms or other kind of time variant networks. And non-convex, we're gonna cover them a little bit over the next lectures. And finally, some references. Any question? Thanks.